I will present some work which we did on the last, let's say, 2 years about the subject for today will be about green measures, and also for Markov process at the first, and then we will also speak about time change in Markov process. Okay, so that's but I will concentrate mainly on the first part, green measures for Markov process, and then the other one will be somehow a kind of I don't want to say a consequence, but yeah, I mean the results somehow are a consequence of some other old results which we produced in our group. Okay, so of course this is a joint work with Professor Yuri Kondratiev, also with Professor Anatoly Koshubey, although the green measures are only with Yuri, yeah, but we somehow use the works with the Professor Koshubey on this works. Okay, so let's go. So this is somehow the outlook of the talk. So the first part I will just speak in general. Yeah.
Disappears your slide. I do not see.
Slide disappear?
Yes.
No.
Okay.
Now it's okay.
Okay, then I will just change the screen, because this browser, this you know, this what I'm showing is not the best somehow. I could put maybe here like that, but it will not improve. I will change the things. Okay, so one moment. I will just change the.
Oh, now.
No, I just want to put this in full screen. Full screen here.
Oh, okay.
Yeah. Okay, so that's it. So here, the first section will be somehow a general, the general framework of the in order to handle these green measures, and then we concentrate in some examples, some well-known examples like this jump generators and Brownian motion, for example, but maybe also for some other processes possible to do this kind of approach. Yeah, and then on the section 3. I will speak about the green measures for time change Markov process. Okay. So let's now fix the problem. What is the problem which we want to solve? So we start with the Markov process xt, starting from x in our RD. Okay, and then we define for a function f. We define what is called the potential of this function f, and the potential is defined using this formula 1, which is the integral with respect to t. T is the time parameter of the process, and then you would make an expectation and you apply f to the process f of x. Yeah, so then you compute this expectation and then you integrate. Okay, so that's called the potential. It's a well-known theory of potential in stochastics, for example. There are books about that. Yeah. And now the question is how to handle such kind of objects, you know, and in general, you see, for a general Markov process, this is not so easy to handle, depending on the class of functions and so on. And what we did somehow was to just transform this potential in the following way. We just write this integral form, so in this other equivalent somehow way, where here it appears a function which depends on x, and it is a measure. It is a measure in RD. Okay, and this measure is a kind of is a fundamental solution for the equation minus LV equal to f, where L is the generator of the process, the Markov process. Okay, So, and we can see this measure as the green measure for this operator. Yeah, so there is this kind of relation between the potential and the green measure, and the solution of this equation here. Yeah, and the fundamental solution. Yeah, so we have this such kind of let's say relation. Yeah, but relation in commas, because it's not really a relation, but it's a kind of comparison between these two concepts. Yeah, the potential is for the green measure as the solution of this equation involving the generator is for the green measure. Yeah, so the fundamental solution. Yeah. Okay, so that's the, so, and then we want to compute the green measure for different types of process. Here we just handle these two, which I mentioned, but you know, this kind of approach maybe we can use for other type of process. Okay. So under this general framework, which I mentioned, is we can just use this semi-group type, semi-group in Banach spaces, for example. Although here Banach spaces here, for example, we just mention, you know, different types like bounded functions or continuous with which are bounded, or the LP spaces for p bigger or equal than 1. Okay, so and a Markov semi-group is a family of linear operators in one of these Banach spaces. Yeah, and as more or less everybody knows, this semi-group satisfies this following set of axioms, which is it's well known. So it's a linear operator. You know, in 0 it's the identity operator of the Banach space, and then when number 3, when t goes to 0, that gives the f for any f on the Banach space. And then you have number 4 is the semi-group property, and then it is positive. So that means if you apply to a positive function, then it remains positive. There is also this conservative property, which is if you apply the semi-group, this family to 1, to the function 1, then it also gives 1. Okay, so this is somehow the general setup. And then still here inside, what is the relation between the, you know, the Markov process and the semi-group? Yeah, so a semi-group is associated to a Markov process if we have such equality here. So the TTF on X is equal to the expectation of F applied to X, which you can write, you know, just using the transition probability of the Markov process. You can just write as the integral in Rn F, and then you have this PTX dy, where this PTX dy is the probability of the transition. Yeah, starting in X, and then to be inside of to be in B in the time with a positive time. Yeah, so that's so somehow the definition, I mean, the transition probability definition of the Markov process. Okay. So, and then, of course, the idea is to reconstruct the green measure, which we want to handle using such a transition probability. And, you know, first we have such a relation between, you know, how to write the transition probability using the semi-group. You just compute the semi-group on the indicator function of a Borel set. Yeah. And then it is easy to see that our green measure is nothing else than the integral in T of the transition probability PT x dy. Okay. And of course, this measure does not exist all the time. Yeah. And so it may exist also as a random measure in RD. And in that case, we can write this measure in terms of a distribution. Yeah, so you could just write with a kind of density, but this density is a distribution. Yeah. So So the definition which we then give is the following. So the green measure for a Markov process X with probability, so probability, transition of probability PTB, yeah, is defined in this way. So the green measure on, as a measure, yeah, on B is just the integral 0 infinity PTX B dt, yeah, for any Borel set, any bounded Borel set. Okay, or you could also write in this also into this integral formula, integrating against some function, you know, continuous function with bounded support, for example. Yeah, so then you have such equality here. Okay, so the integration of the green measure against the function, yeah, so it's equal to the integral of the function against the transition probability. Okay, of course, this integral should exist and so on. Yeah, so I don't claim that this kind of equalities, they exist all the time. Yeah, so it depends on each case. Okay, so from the relations of the semi-group, of course, we can also get this equality here with this equality number 2, which is somehow the green measure is a kind of you know, it's related to the inverse of the generator of the process X. Yeah, so you can write in this form here. Yeah, so you can write, you see, the integral in RD of a function with compact support. Yeah, so against this green measure is nothing else but the inverse of this operator L. Yeah. And looking in another way, you can see this as the fundamental solution. The green measure is the fundamental solution for this operator, for the operator L, and then you write it like that. So you write this as a kind of density, but as I said, this density may be a distribution, yeah, positive generalized function. So if you just see this measure as a random measure, then you can write in this way. Okay, so somehow this is the general setup. Now let's go for some examples. Okay, so the examples which are more or less known for the audience here, some of them already worked a lot on this direction. So this first example is these jump generators. Yeah, jump generator. So first we have to introduce the jump kernel, and then we define the operator L. The next slide. So you see, for the jump kernel, we use such assumptions, which is symmetric, positive, bounded, and integrable. And in addition, we ask also for here I use this condition, which is the Fourier transform is L1. And the second moment. There is also other type of conditions which imply such one, but for us this is sufficient, or is a consequence of some other condition. But anyway, so that's the conditions on the jump kernel of the generator, which we will construct later on the next slide. Okay.
Excuse me, I have a question.
Yeah.
Do you assume that the dimension of the space D is greater than 2?
Yeah, I mean, the cases which we will under typically will be greater than 2. Yeah, that's right. Yeah. Okay. So if you have D equal 1 or 2, then the green measure has to be the green measure typically does not exist, and then you have to modify the definition. Yeah. Exactly. You can define maybe using, kind of normalization or things like that. Mm-hmm. So anyway, I will speak about that on the section about time change. Yeah.
Mm-hmm. Okay.
For example, we could also see this. I mean, if people working in local times, we could also see this as the measure of the local times. And more or less, this is well known that depending on the dimension, you see, typically dimension 1 is okay for the standard type of process which we know. But if you increase the dimension, then starting from 2 already, we have to let's say, renormalize in different ways. There is different ways to renormalize, and here the effect is more or less the same. Yeah, I think that's what you mean. But you are right. Of course, dimension is very important, critical. 1 and 2 are critical dimensions, and then for these examples, we always have the d bigger or equal than 3.
Maybe in small dimension, you should modify this last condition on the dispersal kernel. But okay, now I understand. So you consider d is greater than 3.
Okay, so then the generator for this jump kernel is defined in this way. So it's a convolution operator, yeah. So you just convolute A with the function f. Of course, f is one of the spaces which we mentioned, yeah. So and then you just subtract also the identity, yeah, f of x. So you can define this, for example, in all this, you know, either in L2 or LP with b bigger than 1. And this operator is also a bounded linear operator, okay? And we call this operator L, the jump generator with jump kernel A, okay? So, and the Markov process associated to this operator is the compound Poisson process, okay? So this is the old stuff, which is also known. And in addition, if you just compute the Fourier transform, of course, you get nothing else, you know, then the multiplication operator. So the Fourier transform, or the symbol of the operator, is nothing else than the multiplication by the Fourier transform of A minus 1, which is the consequence of the definition and the convolution, yeah? Okay, so, and this operator was already, I mean, studied by, you know, by many people, yeah. Most of you are already work on that. And here I have 3 publications. There is more authors, but they are not all included here, otherwise they will not fit on the slide. But these are 3 papers from 18, 2 from 18 and 1 from 17. And I will use some properties of these papers in order to derive the formula or the identity for our green measure or green function, if you want. Okay, so at first we denote G lambda. Lambda is a positive real number. We denote G lambda xy, the resolvent kernel for the resolvent operator. So this is the lambda minus L power minus 1, okay? And from the papers which I mentioned before, this resolvent kernel can be written in this form. So you have a constant, 1 over 1 plus lambda, and then you have the sum of 2 parts. One is the Dirac measure or Dirac function, yeah? And then the other one is a function G, which depends on lambda, and then on the difference between x and y. Okay, and this function G we can derive from the formula for the operator L, and it's given in terms of this series, which is AK. AK is I denote this. This is the power, the convolution power K times. Yeah, so you convolute the kernel K times, and then you have the series from 1 to infinity. Okay, and the lambda is a positive number. Of course, because we are interested in the green measure, so we are interested essentially when lambda goes to 0. Yeah, our interest is when lambda is equal to 0. Okay, and you see this resolvent kernel. We have 2 parts. One is the singular part, and the other one is the regular part, which we call regular part. We call the G lambda. Yeah, regular, no, Homan G lambda, and we will concentrate mainly on this regular part for this examples, which I will show on the following. Okay, so that means this G0, this last equation G0 when lambda equal to 0, somehow is the, you know, this Dirac plus the other function G on the point 0. Okay, and if you put this on the point 0, you see G0x is just the series of AK, where AK is the convolution of the jump kernel, K times, yeah. Okay, so that's the representation for this resolvent kernel. Okay, and now let's see what happens when we choose, when we handle some example. What happens essentially to this G0? So we are concentrated now on this G0, and the first example, somehow one of the most simple ones, are this Gaussian kernels. Yeah. So if A is just this Gaussian kernel, so it's a constant times minus the square of the norm of x, and you divide by 2, and then you can still multiply by another positive constant. Okay. What happens in this case? What happens to G0? G0 is smaller or equal than the same type of expression. So it will be another constant C1, and then you still have a Gaussian type decay. Yeah. So, but here I have an explicit that dimension is bigger than 2, bigger than 3, bigger or equal than 3. Okay. So the proof essentially is based on the fact that we can compute directly this convolution kernel. Yeah, we can compute this k times, and then you plug this in the series which appeared before. Yeah, so you plug this in the series, and you have to estimate, of course, you have to estimate a little bit, but that's not too hard. So you could also, using this explicit formula, you could expand also the exponential, and then you can get somehow very easy this estimation here. Yeah. So this is the case when we can compute very easy this convolution kernel. Huh? So I will not give all the details, but somehow in the middle it appears somehow a zeta function, but the zeta function you can estimate depending on d. Yeah, and there we need d bigger than 2. And that's somehow the point where we need this d bigger than or equal than 3. Okay, so that's the first result. And then there is also this exponential tail. So it's exponential, but now it's a linear, it's exponential with a linear in the power. Yeah, so we have a is equal to a constant, then exponential minus delta and modulus of x. Okay, so and the result for that is also the same type. You get also the same type of result. It said G0 is smaller than a constant times exponential, another constant times the modulus of x. Okay, and here I use heavily this estimation in one of Yuri's papers on 2018, that the convolution kernel, for such type of kernel, the convolution can be estimated from above with such bound, which is a constant times n power d minus d over 2, and then you have the exponential of some minimal, some minimal between the modulus of x and some other thing, and this is sufficient in order to get an estimation. An estimation on the an, So we can make another estimation, a bigger estimation, by you just make the sum of the two things which appear on the minimum, And if you plug this on the series for the G0, then you can obtain the estimation from the proposition. Okay. So that's so of course there is other cases, for example, like heavy tail or lighter tails. As far as the second moment is finite, for example, for one of them is not, this is not the case, but somehow we did not made at least one where the second moment is finite, but maybe we can also do such kind of estimation also, I guess for the light tail, I guess. If A is a light tail, then I guess we can make such kind of estimation also. So I will not mention this now. So let's give another example, which is the Brownian motion. So it's also well known. So the Brownian motion, the generator for the Brownian motion on that case is the Laplacian, okay? And we are interested on this process here, y, we depend on f, which is the integral between 0 and infinity of f applied to bt dt. Of course, in order to obtain the green measure, we have to take the expectation, yeah. But then we can take both this expectation and change with the integral, yeah. So this is for a certain class of functions, f, of course. And as a class of function, we define the following Banach space. Just put it CL. So these are the functions which are continuous and also L1. Okay, bounded and L1. Continuous functions, bounded and L1. And on the norm on the space, you just make the sum of the two, L1 and the L1 norm and the supremum norm of the function. Okay. And then the following result or the sum of the proposition. So if d is bigger or equal than 3, then the green measure of the Brownian motion is given in this way. So you have g0 x minus y dy is equal to, you have a constant which depends on d, and then you have this fraction x minus y power d minus 2. And yeah, so the proof is based somehow on this representation of the expectation for the integral of y of f, which is this the inverse of the Laplacian. Okay, and this integral on the right hand side we can estimate using the decomposition of RD in two parts, two disjoint parts. One is if x minus y is smaller or equal than 1, and the other one is if it is bigger or equal than 1. Okay, and here on the first integral, you use the integrability or the local integrability of this power here, and then you for f you just use the supremum norm, and for the other one you constant and then you use the integrability of f, and putting together you can just make estimation by a constant times the norm of f on the space on this Banach space CL. Okay, which has the norm is the sum of the two. So okay, so that's the green measure for this also, I mean, Markov process, of course. Yeah. So concerning the time change, to start with the Markov process X, and then we make a time change of this process. So first, before we make the time change, let us fix some notation. So here, for this process, for this Markov process X, I introduce this function in T and X, which is the expectation of a function. A function should be a suitable function. Yes, again, f of x of t. So the small x is the point where x starts always. Okay, and this function, of course, is the solution for this Kolmogorov equation L, which appear here. This is the operator associated to the Markov process, the generator of this Markov process. Okay, so that's the starting process. And now what we do is the time change, the time change, we call it E of t, and we take an inverse of a subordinator, yeah? So somehow these are the most interesting cases, okay? The inverse of a subordinator. And the subordinator S, it's independent of the original process X, okay? So, and then of course we do as before, we introduce another function which we call v as the expectation with respect of a suitable function f of the process y. And now what happens is, you see, before the function associated, the u function associated to the Markov process satisfy this Kolmogorov equation. And now when you make the time change, the function v will satisfy a similar equation, except that the derivative in t we change for a fractional derivative. And the fractional derivative here, k is this kind of order of derivative, which is the L1 function. So actually this is a generalized fractional derivative or differential convolution operator. Yeah. So so this kind of generalized derivative was introduced by Professor Koshubey in 2011. Okay, you see the L is the same. Okay, and then you have the function v. Okay, and of course you ask where this where k comes from. Where this k comes from? K somehow is associated to the subordinator. So we can define k using some characteristics of the subordinator. So we have to write the Laplace transform of the subordinator, and then it appears the Laplace exponent, and write it in the Levin-Kinchin formula, and so on and so on. But it's possible to do such kind of things. Okay. And now the question is, another thing which is also known for this case is the outright, this function v in terms of the original function u, and this is the so-called subordination formula, or subordination principle, if you want, and which says that the formula, the function v is the subordination of u with respect to this function, which I denoted here g t tau. They say this g here has nothing to do with the green function before. So it's, this g t tau is the density of the inverse subordinator. Yeah, this et. So this is the inverse of the subordinated s. Okay. Of course, for example, for the alpha stable subordinator, this gt tau is known. Also, if you make sums of them, sums of let's say independent sums of two alpha stable subordinators, this is also known, and so on. For each case, it's possible to identify such function. Yeah, but it's not always easy to handle, let's say. Yeah, so this gt tau is not so easy. I mean, it's what we know about this gt tau in general is not a lot, but for the for the classical case alpha stable, so a lot of things are already known. Okay, and now, of course, if you denote the marginal densities of x and y, x is the original Markov process. I denote it by mu tx, and for the other one, I denote for the y, this time change, I denote the nu tx, the marginal densities of x and y. So then we have such a nice relation, which is the marginal density of y is the subordination of the marginal density of x with respect to the density gt tau, again, which is the density of the inverse subordinator. Okay. And using such a subordination identity or equality, we can somehow compute the green measure of for this case. We can show these things. You see, let me just show you what is going on here, which I call it trapping effect. So Yuri on the last seminar last week, he spoke about that. So you see, we start here. I hope that you can see the pictures. Yeah. So on the left side, I have my subordinator. Yeah. So it's an increasing process which has some jumps. Yeah. I put these jumps on red. You see, on the left side, and on the right side, the picture on the right side, I have my inverse subordinator. Yeah, and what happens is, you see, when the subordinator it jumps, the inverse subordinator it remains constant. Yeah, and then it increases, and then if the other one jumps, it also remains constant, and so on. Yeah, and what happens is this kind of this trap or flat period. Yeah, this flat periods. You see, if this is describing the evolution of particles, somehow the particles on this flat period they will be somehow blocked. Yeah, so we call it immobilized. Yeah, by this trap. Okay, and somehow this trap has the somehow influence on the dynamics of the process. Somehow, you see, what we try to understand is what is the influence of these traps on the behavior of this process Y, or the time change process. Okay, so that's somehow the idea behind. So so here is somehow a slide about the assumptions which we need in order to derive the results. So we see the subordinator, which I denote by S. It has a Laplace transform in this way. So here we have a Bernstein function phi of lambda, and we can represent this phi of lambda using the Levin-Kinchin formula. And so this is a simplified version, which, it's without drift. We have no constant, no drift. Yeah. We have only jump parts. Yeah. So, and then we define K using this, what we call Levy measure, which is sigma. You see this K, which enters on the order derivative, is defined as the measure of the interval T until infinity. Okay, and by K, calligraphic K lambda, I denote the Laplace transform of this kernel K, in the point lambda. And then there is here this assumption, which is the Levy measure as a completely monotone density. So this means this function, the density with respect to the Lebesgue measure, should satisfy this, this equality, this assumption here, or inequality. -1 power n for any number, for any natural number, multiplied by the derivative of order n should be equal than 0. Yeah, this is true for any number. And in addition, the calligraphic K, or the Laplace exponent should satisfy this equation here, which is on 0 it goes to infinity. I speak about K. On infinity it goes to 0. Okay. So this reflects on the Laplace exponent on this way. So it goes to 0 in 0 and then goes to infinity on infinity. So there is a relation between the two. Yeah. So K is phi divided by lambda. Okay, now the green measure. So the green measure, so here is the first bad news. The green measure for the time change process does not exist. Yeah. So the green measure is defined in this way. So it's the integral 0 infinity, and here is the one-dimensional marginal. Okay, and then you integrate with respect to t. Okay, and so under the assumptions, which are stated before, and for any dimension, the green measure of the time change process does not exist. Okay, so I mean, the reason why it does not exist, it is a consequence of the subordination formula. So if you just write the subordination formula, which we saw before here on that slide, this formula 10, if you substitute this formula on the green measure here, and then you apply Fubini, and then you fall on this integral from 0 to infinity and the density of the inverse process. And this is nothing else than the value of the Laplace transform of the kernel K. And this, by assumption, which we put on the slide before, this is infinity. So on 0 goes to infinity. So then we cannot, this integral for the green function does not exist. Okay, so here we need something to do something in order to define the green measure. And the idea is to use the renormalized green measure. Here we use this kind of renormalization. We just define a renormalized green measure as the limit of this quantity. So integral 0 until a certain positive time, and then you integrate, this one-dimensional distribution of the time change process, and then you have to normalize it by a constant, or by this quantity NT. And the question is how to find this quantity NT such that this limit exists. So that's that's the key point of this result is to find this NT. The NT is nothing else than the integral from 0 to t of this kernel K. The kernel which is used on the fractional derivative integral with respect to the variable. Okay, and if we use such a normalization, then our renormalized green measure coincides with the green measure of the process. Okay, so that's a kind of a miracle, and the proof of this result, it relies on a result which we proved before together with Professor Kushubey, which is the following. So of course, again, you have to substitute, on the formula before, you have to substitute the one-dimensional distribution of y by, subordination principle, and then you make change of integrals and so on. And then somehow you get such kind of a limit, this limit here. And this limit, somehow, this was a paper which we published in 2020 in Dynamical Systems, which is the integral 0t of the density divided by the integral 0t of this kernel, it goes to 1. And somehow that's the key point to prove the theorem about the renormalization of the green measure for the time change process. Okay, so I don't know if there exist other type of normalizations which we can also prove the existence. So that may be one possibility. So for example, I know from local time that you can also have, you can have multiplicative normalizations, or you can have also other type of normalization. So maybe here we also could have such other type of normalization. But somehow I did not explore also this kind of facts. Okay, so that's and as I said, maybe this technique can be used for other type of process. So here I just mentioned some of them, but maybe you can also use for other type of process which somehow appear on the applications. So now I have some other references which are most heavily used on this work, which I finished of presenting. So you see this essentially number, the first one and the last two. So these two we used in order to get these estimations of the jump kernel. So the other some of our works where this presentation is based on, there is another one. So that's a classical work from Scarwood. So that's a summary. What somehow what we did. Somehow, if you have now, now start the time of discussion. Okay.
Thank you very much.
Thank
Any questions?
May I give some comment?
Yeah.
Jose Luis, please came back to definition of jump kernel.
Okay.
It was much before.
Yeah, it's a little bit before. I know.
Yeah.
Jump kernel here.
Yeah. So, Jose Luis did explain existence of green measures for some concrete classes of jump kernels. But he has hidden main result what we have. Main result was, you forget, main result was that for any kernel of this class, green measure exists.
Mhm.
Yeah? We have such theorem. If you have any jump kernel of this class, and you consider corresponding Markov process, then green measure exists. It was, I think so, main result in our paper. Not only example, but for all the class.
Mm.
Do you agree with me?
Yes, somehow I missed this result.
Yeah.
I missed this result.
Probably it should be topic for another talk, but it is
okay.
really elegant result that it is not related with concrete examples. Concrete examples are nice, of course. It is always nice to have concrete bound and so on, but general result is the following. For any jump kernel of this type, what we have on screen, green measure
Okay.
full stop.
Okay,
But
okay.
here
Yeah.
I have another comment which probably has also physical meaning. We have the following. We have random walk or jump process or compound Poisson process with some jump kernel A. In physics, such processes people call diffusion. Yeah, Dima?
Yes.
As any random walk, yeah? But here we need assumption about finite second moment, yeah? You see?
Yes.
Last assumption. Of course, it restricts class of possible diffusions, yeah?
Absolutely.
But using proof of theorem, which Jose Luis forget to show, we can see that we can eliminate this condition for finite second moment. Actually, we can consider any jump kernel with some assumption about asymptotical Fourier transform at 0. And green measure will exist, but we will have more delicate relation between dimension and asymptotic of Fourier transform. I think so, from point of view of theoretical physics, it is reasonable to mention that we do not restrict in principle ourselves. It may be jump kernel with heavy tails without second moment. Nevertheless, green measure will exist, but we need control dimension more carefully. So,
yeah, so I agree. I mean, this is a consequence of the formula or the equality for G0. Yeah. And there we use the second moment. But of course, as far as this integral exists, so that's you can eliminate this condition. That's right. I mean, yes, this somehow I missed this in my presentation. That's right. But you are right that for such kind of jump kernels, the green measure exists, and there exists an explicit formula for the G0, which is this, and
in terms of Fourier transform and so on.
Yeah. Of course, you are right. Yes. If you take out the second moment, then you need some more conditions on the Fourier transform, such that the integral exists. Okay.
So I think so sometime we should come back to this question, because it is really only one general result what we have now. It is not related with exams. Exams are nice, but we have general result, and
Okay. Okay.
that's it for any kernel. Probably we should discuss with you generalization, and sometime later we can discuss this question.
Mhm.
Thank you very much for presentation. I like your talk very much.
Thank you. Could I also make a kind of remark
Yeah, yeah.
Yeah.
from the point of view of physics, so to say?
You should. You should.
Let me just explain you what you are doing, guys, in terms of very simple models of, like, random walks on graphs.
Yeah.
So suppose so first keyword, green function.
Yeah.
What the physicists really understand at this very moment.
Yeah, yeah.
When people start to think about and talk about green function, they want to be able to measure distances, to make some elementary geometry and so on.
Yeah.
Now, what Yuri has explained us just say a minute ago, saying that Fourier, it's possible to regularize this this requirement by doing something with the Fourier transform at 0.
Mm.
So if I want to use random walks or diffusions, if you want, to measure distances, I have a problem. I want to measure distances between 2 points by time when what it takes for a random walk or diffusion particle to get from A to B, from between this. And here there is a problem because this particle might make loops.
Yeah.
As many loops as whatever. What people do in simple applied mathematics setting, they switch to self-avoiding random walks. Loops are not allowed. That is what Yuri told. Let us get rid of Fourier transform at 0, so loops, actually, right? So now we have self-avoiding random walks, what corresponds to, if I consider a Laplace transform, I mean, inverse of the Laplace operator on the lattice, it is not invertible, so I should use Drazin generalized inverse. In this case, to get rid of these loops. And finally, I have what people call these first encounter quantities, first passage times, first heating times, getting rid of all loops. And now what Hazelwish told us, now I change my time randomly and I got another problem. I can and stay, I mean, this random walker could stack in this particular point and stay there forever. And move next time and then stack there forever. And I don't know for the moment how to regularize such a story. So this is what I actually learned today. Mm-hmm. And I really grateful to Jose Luis because he just explained, for instance, many situations which I did not recognize before in this discrete setting concerning generators and for instance, subordinators, how they might work. But now I just, while listening, I just rewrote it in a discrete case. It's very interesting and I never thought about it. Yeah, thank you.
I would like to add to your comments some remark. Such self-avoiding random walk, self-avoiding Brownian motion, self-avoiding fractional Brownian motion are extremely important in theory of what people call, Luis, what you are doing with stride?
In polymer physics.
Yeah.
Yes, okay, yes, I understand, because they could not cross, yes, indeed.
Because some quantity are explained by expectation, not self-avoiding and so on.
So there is this kind of concept of penalization, so if he comes back, he penalizes in order to that he comes back, you see. That's the idea.
So it is really deep problem in physics, in theoretical physics, how to compute characteristics of such objects. And especially recently, Jose Louis, Streit, and company are working with situation of fractional Brownian motion. Usually in physics, people use Brownian motion and meet some problems, yeah, which are well known. In higher dimension, it is really mystical. But for fractional Brownian motion, people have more hopes. But long ago, I proposed to such people that why you use Brownian motion or fractional Brownian motion? You should use random walks, yeah, as process, basic process. It will be more natural for your problem. But as I understood, they do not accept my proposition. But you see, after your comments, Dima, probably it is really reasonable to look to random walks instead of Brownian motion, yeah, of different type Brownian random walks. Try to analyze not self-avoiding and apply to problems what people study in physics, yeah, in theoretical physics.
Okay.
Okay,
Yeah,
just
sure.
comments to your comments, yeah.
Thank you.
It may be exciting, yeah.
Yeah, absolutely. I mean, I guess that.
Why
at least,
Brownian motion only? We have another diffusions. We have random walks with different properties. And if you have random walk with very, very slowly decaying kernels, self-avoiding should be very natural property, yeah, under very weak renormalization, because you are particularly jump far, essentially, yeah, and to come back, probability is very small.
Yeah.
It is dark observation, sorry for that, but maybe it is interesting question.
Okay, thank you very much. Any other questions, comments?
May I also ask, so as far as I understood, the reason to consider, the interest to consider inverse subordinator is to have non-Markov process. So because of this, you consider the function which has constant intervals, right?
Yeah.
If this function is strictly monotone, strictly increasing, then it will be Markov process, and this somehow is less interesting to a certain extent, right? But what is happening?
I would like to say that if you use not inverse subordinator, but subordinator itself, it will be Bochner subordination, and it will be Markov, and people are less enthusiastic somehow. It will not produce new effect.
It will not produce new effect. But if you consider, if on that, instead of that function which has constant intervals, you would consider increasing function, but slightly. So it will be like on those constant intervals, you will now straight line, but this very little slope. So it will be Markov process, right? Or Bochner subordinator will be possible to see by properties that indeed there exists certain slowdown. So something will, diffusion will be slowly and all that stuff.
Dima, what I assume, you will have inverse subordinator without flat places if and only if your subordinator is strictly monotonic without jumps. But without jumps, probably you have almost no examples. Subordinator as Levy process always typically include jumps.
Okay.
Yeah, it may be problems that probably you can easily describe all subordinator without jumps. It should be in literature, yeah.
Mm-hmm.
It should be very degenerated class of Levy processes. Okay. And question is reasonable, but it will be applied only to very special class of subordinate.
Yeah.
Next Friday, I hope I will give talk in which I will come again and again to this question about what is random time and why random time, how we appear random time. By the way, I would like to thank all participants because, especially because in Germany, in Portugal, and many other places, today is holiday.
Mhm.
Yeah, in Germany it's called,
It's a Saint-Off.
yeah,
We have holiday in schools, Good Friday,
yeah.
but we have holidays on Monday in universities. So there is a difference. You know, in schools, Friday is holiday. In universities, Monday is holiday. In the United States,
Okay.
Yuri,
So-
may I add just a remark? May I, Yuri?
Sorry?
May I add a remark?
Yeah,
Yes,
yeah,
please.
of course.
First of all, I'm happy because you are getting interested on polymers.
Mhm.
But you touched the question of the fraction of the Brownian motion. As a matter of fact, the Brownian motion, it's nice to model the long chain of polymers, but these polymers should be inside of good solvents. The question is if we pretend to model polymers without this question concerning the quality of the solvents. And that's why we are using fractional Brownian motion. On the other hand, there exists a polymers chain, like for example, the N chain, where it's where is reflected the long memory effect. And this
Yeah.
is another motivation to use the fractional Brownian motion. This is the main reason, the two main reasons why we are working on the fractional case.
But if you will take Brownian motion and produce random time change in Brownian motion, it will be again with memory effect, but it will be another kind of memory. Probably
Yeah.
such process, Brownian motion with random time, but not fractional Brownian motion, is another possibility in polymer science.
Okay, here the big advantage is because you have a parameter, the Earth coefficient, where you can control the behavior of the polymer inside of the solvent, independently of the quality of the solvent. That is the main reason why we prefer to work, or until now we have worked with the fractional Brownian motion. This is the main reason.
Yeah, but I would like to say again that fractional Brownian motion is not unique possibility.
No, of course not, Yuri. But if you choose
Probably.
another approach, you will have different technical problems. So you cannot solve all the problems changing the framework, let's say in this way.
Mhm. Okay, thank you.
But I'm glad you are interested on polymers, Yuri. You're welcome to the team.
You are working a lot with Ludwig Streit and other colleagues about this, I know. But it will be interesting to look to alternative possibility.
No, of course, Yuri. Of course, we are open to alternative possibilities. This is clear.
People in physics use Brownian motion, yeah, because they know very well. You use fractional Brownian motion, you are enthusiastic with respect to fractional Brownian motion. What I propose to use time-changed Brownian motion. It is another alternative technique. I cannot say that it is a solution of your problem, but let us try.
Yes, okay. To a certain class of polymers, it's possible, yes.
Yeah.
We cannot exclude that possibility, of course.
Yeah.
Okay. Thank you very much. Any other questions, remarks? So thank you for attending this nice talk. Thank you, Jose Luis.
I have a question. I have a question.
Yes, please, Lifimia.
Can you say an example of the Markov semi-groups that I can see as related to the kernel or Luis?
Again, what is the question?
Take heat equation, and it is example. Take heat equation, and heat equation give you example of Markov.
Any continuous equation is a semi-group.
Again, what is the equation?
any continuous differential equation is a semi-group that a Markov semi-group or that has a,
Parabolic equation is okay. Parabolic
equation?
equations are okay.
Parabolic equations.
any parabolic equation is okay.
Any parabolic evolution equation is in some sense general
Yeah.
example. Yeah.
Okay, thank you, thank you.
Okay. Thank you very much. Okay, so next time, next Friday, we have talk of Yuri. And then week after, we have talk of Mark. I will announce these seminars regularly along with providing the link to YouTube video where we will have, today's seminar. Thank you very much. Have a nice weekend. Happy Easter to those who celebrate.
Also to you.
All the best.
The best.
Bye.
Bye.
Bye. Thank you.
Thank you.
See you.
Bye.
Bye. Bye.
Bye.
Thanks.
Bye.
Ciao.
Right.